Hello, good morning, afternoon. For me, it's morning. Still, I didn't have lunch, so it's morning. Everybody. So today we are gonna start the second webinar, the second presentation. The other day we talked about genomic selection, about the Canadian sheep evaluation system, genetic evaluation system we have here together with genetics and math and other people who participate. And today our invited speaker is Dr. Nancy Stonos. Nancy Stonos is currently a project and research manager in the Ontario Gold, and her current research investigates the interaction between Lentiviruses virus of sheep and Mycobacterium avium disease. Yeah, exactly. Both diseases have a major impact on sheep and goat production, and both modulate the host immune response. So today, Nancy, she's gonna update us with all the research going on, the results she found, and all these very cool things that we are sure that are very interesting for all of us. Again, and as the last day, if you have any question at the last, after Nancy finishes her talk, we will have some time for questions.
Perfect.
Okay?
Yeah. Thank you.
Thank you, Nancy, again for coming. And
All right.
for you.
So thanks everyone for tuning in today. I'm actually still working on my PhD here at the university, so I'm getting really close to finishing.
I'm sorry.
I don't have my PhD yet.
For me, you're already
And because I'm sort of on the home stretch, I'm also working with Ontario right now. So I'm going to talk about some of the PhD work I did, and what I looked at was the interaction between the small ruminant lentiviruses and Johne disease in Ontario sheep and goats.
Oh.
Go to the next slide.
Yeah, you can move.
I don't know. What am I doing?
Oh, maybe with this one.
Oh,
Yeah.
there we go. Maybe it's okay. So to give everyone a brief outline in terms of what I'm going to be talking about, I'm going to sort of give a bit of an overview of what the small ruminant lentiviruses are and what Johne disease is. I'm going to talk about how they affect sheep and goats. I'm going to talk about some co-prevalence work I did as part of my PhD, and then to sort of expand on sort of some of the genetic selection stuff that we talked about earlier. I'm going to talk about genomic selection and the potential for breeding for disease resistance. I'm going to include some information about the high immune response technology that was developed here at the university as well. And I'm also going to add a layer to that and include some information about how stress and immunity work together. And then I'll wrap up with some disease management and biosecurity, and then some cure recommendations. So the small ruminant lentiviruses consist of the Safrine arthritis encephalitis virus in goats and the Lentiviruses virus in sheep. So these are lentiviruses that are sort of in the same family as HIV, but they don't quite look the same when a sheep or goat is infected. They can be transmitted between sheep and goats, and you can actually get multiple strains infected in one animal. So you can have sort of hybrid strains occurring in animals, and then you can also get animals infected with more than one strain. Now, these viruses infect immune cells, and these are immune cells that we call monocytes and macrophages, and they're part of the first line of defense against invading microbes. So what does the disease look like? Well, the small ruminant lentiviruses cause 4 chronic disease states. These include arthritis, encephalitis or myelitis, mastitis, and pneumonia. Now, when a goat becomes infected with CAED, we tend to see signs of arthritis or mastitis. But when a sheep is infected, we tend to see more signs of mastitis and pneumonia. Now, young animals, when they become infected, they tend to, if they show clinical disease symptoms, they tend to exhibit signs of either encephalitis or myelitis. So they might have some neurological problems, like trouble with balance and that kind of thing. So these viruses, once they're in the animal, they have a long incubation period. So that means that the animal becomes infected, and it can take months or years before any clinical disease symptoms emerge. So it's very possible that you have animals in your herd or flock that are infected and you have no idea. So it's really hard to detect this disease because of that. There's also no treatment or vaccine, and animals remain infected for life.
Take it back. We might have to. She's got to take back control. She just lost it.
All right, we'll just
Axel has
get
control.
sorted out here.
Yeah.
No.
Yeah.
You can go.
You know, she can't make the screen work because Axel has control.
You go to the next slide.
I have control.
Okay, there we
Okay.
go. Back on track now.
Okay.
All right, so the virus is transmitted primarily from the mother to the newborn animal, so from the lamb, or the mother to the lamb or the kid. And this is primarily through colostrum milk, and this is because the udder is a main reservoir for the virus. Now, horizontal transmission can also occur, and this is the transmission between animals of the same generation. So this can occur through contact with bodily secretion, so nose-to-nose contact. But sexual transmission is also possible with these. Okay, so to switch gears now to talk a little bit about Johne's disease. Johne's disease is caused by the bacteria Mycobacterium subspecies paratuberculosis. So because that's a bit of a mouthful, we abbreviate that to MAP. This is also a bacteria that infects the same sort of immune cells that we saw with our viruses. So they infect monocytes and macrophages, which again are part of the first line of defense against invading microorganisms. This is also a very slow growing bacteria. So what happens is that this bacteria enters the cell, and I have it sort of shown here, is that the red immune cell is actually labeled bacteria. So we use the fluorescent probe to label the bacteria, and we can see it sort of hanging out inside these cells. Now, there's a couple of ways that MAP survives by doing this. So basically, once it's inside the cell, antibiotics can't really get in there and do anything about it. So it kind of hides and avoids detection by the immune system. So it alters the function of the cell to sort of protect itself and continue to grow. Now, it grows very, very slowly. So once it's inside the cell, it can take a long time before we get high bacteria numbers to actually be shed in the feces. So the disease is a little bit different from what we see in cattle. So in sheep and goats, we tend to see that there's a lot of chronic wasting, and there may or may not be diarrhea associated with it. And this is because we have this chronic inflammation that occurs in the small intestine, which leads to malabsorption and wasting and potentially diarrhea. Now, the primary mode of transmission for this is also through colostrum and milk, but it's also primarily shed through the fecal oral route. And this is because the bacteria grow within the intestinal lining and then are shed out into the feces. So if we compare these two diseases side by side, what do they look like? So the small ruminant lentiviruses cause chronic inflammation. So this is where we see our arthritis or our mastitis or our pneumonia in these animals that are infected. It's because they get lesions that form in those tissues that are a result of basically a ton of different immune cells coming in and causing that inflammation. So both of them are chronic inflammatory diseases. They both infect the same type of immune cells. They're both shed in colostrum and milk, and they're both very widespread in the province of Ontario. So a couple of years ago, we did a prevalence study in Ontario dairy goats and found that the prevalence was 80.4%. And then some previous work done by Dr. Kathy Bowman here at the university as well identified that in dairy goats, about 79.3% of herds had at least one infected animal, and 57.1% of dairy sheep flocks had at least one infected animal. So there's a lot of herds and flocks out there that have these infections. So what we wanted to do is we did a little bit of a prevalence study to see how many animals are actually infected with both diseases. So we sampled 28 goat farms from across the province of Ontario. 20 animals were sampled per farm, and from there we collected blood, feces, and milk. We did an ELISA test on the blood, and then we did PCR, and we cultured the feces. Now we did the same thing with our sheep. We had 19 sheep farms with 20 sheep per farm, and then we also collected blood, feces, and milk, and did our ELISA, our PCR test, and our fecal culture test. So in terms of our results, we found that basically 7.2% of animals in the province of Ontario were infected or tested positive for MAP. And 57.1% of flocks had at least one infected animal. When it comes to the virus side of things, we saw that 41.3% of animals were infected with Lentiviruses, and 78.9% of flocks had at least one infected animal. So when we look at our co-infection numbers, we had really low numbers. So we actually found that 3.4% of animals tested positive for both infections, and 36.8% of flocks had both infections present on farm. So these numbers are actually a bit of a, or you could argue, a bit of a good news story because they're much lower than what we anticipated. But there's a couple problems with these numbers. One is that it's very difficult to detect MAP or Johne disease. The tests aren't very good. We use the fecal culture test to do the analysis with this because it's supposed to be sort of our gold standard test. Unfortunately, though, it's possible that some of those animals may not have been shedding bacteria at the time of sampling. And there's other problems with the test too when it comes to things like contamination and other things because it takes so long to simply grow the bacteria. So even though these numbers are low, it is suspected that they're quite a bit higher than what is recorded here. So it's important to note that these are just the animals that tested positive. It's not necessarily a true representation of how many actually have the disease. And this is sort of a graph just to help visualize the data. So this is our frequency distribution of Lentiviruses and MAP in Ontario sheep flocks. So we have our number of farms along the y-axis and the percentage infected along the x-axis. So quite a few farms actually tested with a prevalence of 0% for both infections. And then for maybe there's a little bit of variation in between, but they tend to be, for Johnes in particular, they tend to be skewed on the low level. And that's probably because of our tests. We're probably not detecting this very well in these animals. For maybe though, it's also important to point out, so we also had several farms that tested with a prevalence of 100%. So this is kind of similar to some of the other work we've seen in goats, where some farms do a really awesome job and keep these diseases off farm, but others not as much, and they struggle with trying to maintain healthy populations. So when we look at our goat data, we found something that was a little bit interesting. So for our Johnes infected goats, we had 18.3% of animals that tested positive, and 79.3% of herds had at least one infected animal. For the viral side of things, we had 80.1% of animals test positive for CAEV, and 89.3% of herds had at least one infected animal. Now, when we look at our co-infection, our numbers are a little bit higher from sheep, but still not crazy high. But we found that 14.2% of animals were co-infected, and 71.4% of farms had both infections present on farm. Now, again, these numbers aren't crazy high on the animal level, but if you look at our Johnes infected animals and then look at our co-infected animals, 90% of our Johnes infected goats also tested positive for CAEV. So this suggests that maybe those animals that are co-infected are maybe shedding more bacteria because maybe we were able to detect it a little bit easier here. You can't say for sure, but it's possible that maybe these animals are having an altered immune response to these infections, and it's causing them to be either more susceptible to other infections, or there might be something else going on. So This is our frequency distribution for CAV and MAP in Ontario Go. So this is a little bit of a different story than what we saw with our sheep. The prevalence of CAV in these animals is quite a bit higher. We have a lot of farms that tested with a prevalence of 100% or between the 90 to 99% range. So there's a lot of farms that almost all of the animals are infected. There's a couple of farms that are also doing a really awesome job in keeping this disease off farm. And then we've got a little bit in between, but they tend to be more on the high side. Now for yogis, we also see, it's not as obvious with the sheep, but we also see this skewed distribution towards the low end of the prevalence sort of spectrum here, which suggests that maybe we're also having a hard time in even detecting the infection. But we'd have to follow up with it just to make sure. Okay, so we've talked about a couple of different diseases. Now I'm going to talk about the potential for breeding for disease resistance. So I'll talk about genomic selection, and then I'll talk about breeding for enhanced immunity. So to jump right in with genomic selection, the first thing you need is your reference population. So establishing a really good reference population with a lot of animals is really important to start off with. From there, you need to genotype and phenotype your animals. But here, this can get a little bit tricky, especially for some diseases, because you need to be able to reliably identify a phenotype associated with the genotype in order to sort of implement this program. So once we genotype and phenotype our animals, we can identify marker genes, calculate breeding values, and make selections. And there's a couple of pros and cons for using genomic selection for breeding for disease resistance. The pros include that it induces disease-specific resistance. This is a permanent change, so it doesn't undo itself after a couple of years. We can see improved health, fertility traits, reduced use of antibiotics potentially, and a couple of the other pros is that this isn't a new technology. This is something that's been used for a long time in our other livestock animals. So it's something that we could easily develop for our small ruminants. And it comes relatively cheap if you've already established a good system for recording data and collecting information. Unfortunately, though, the con to that, though, is that it can be quite expensive if you're starting from scratch. And one of the things I am going to emphasize here is that the disease or the genes that confer resistance to one disease might not be the same for all of the diseases. So if you are going to use genomic selection for breeding for disease resistance, you need to make sure you target more than one disease, which can be a little bit tricky with our small ruminants because there's a lot of diseases out there. Now, the other option is to breed for overall improved health. So what they do, basically with the high immune response technology, is that they select animals based on their immune response, and they breed those animals with improved immune responses to help benefit sort of the next generation. So it targets the immune system so that you get this broad-based, more generalized protection against a variety of different diseases. So basically, what we do, or what they do for this, is that they assess a couple different parameters in the immune response. So they look at antibody levels, and they look at cellular function. So antibodies are really good for protecting you against sort of environmental bacteria, so things that cause mastitis. And then the cells, or the cell-mediated sort of immune response, is really good at dealing with things like viruses and the bacteria that causes tuberculosis or Johne's disease. And then we've kind of included passive immunity here because this is really important in our ruminant animals, because our ruminants, so calves, sheep, goats, they're not born with a fully developed immune system. So they get their immunity from their mom in the form of colostrum. And this is because the colostrum is full of antibodies. So when it comes to sort of assessing whether your animal is a high, average, or low immune responder, basically they look at their antibody responses and they look at their cell responses, and then they rank them as high, average, and low, and then use the high immune responders as breeding stock. So this is some data taken from the cow side of things. So this is something that is available in cows at the moment. And basically, a couple of the benefits of being a high immune responder is that they found that those animals had decreased occurrence of mastitis, metritis, ketosis, and retained placenta. They had improved vaccine responses. They had better hoof health. There is a beneficial association with herd life and longevity. But I'm going to point out a couple of things here. They were less likely to be seropositive for paratuberculosis. So this is Johne's disease. So these animals are less likely to test positive, so maybe they're less likely to get these infections. And they also had improved milk and colostrum quality. And this is also really important because that improved colostrum quality is going to provide a really good start for that newborn animal. And then another layer to this is to look at stress responses. And this is something that Dr. Caro's lab is currently working on here at the university as well. So they're currently evaluating the influence of stress responses and immune responses on resistance to parasites in sheep. So stress and immunity work really closely together, and they tend to help balance each other out, or stress in particular will help keep everything sort of balanced out. So it will influence things like inflammatory responses and antibody production and things like that. So they do work together. So hopefully in the next couple of weeks, you guys will hear more about this. So I won't talk too much about it now. And then to sort of kind of wrap up a little bit, so I've talked about the diseases. I've talked about a couple of ways that we could potentially breed for disease resistance, but disease resistance doesn't happen overnight. So we need to really focus in the meantime on disease management and sort of farm practices that will help reduce the transmission of these diseases. Now, luckily, when it comes to Johne's and the small ruminant lentiviruses, the disease management practices that work for one will also work for the other. So when it comes to Johne's and our small ruminant lentiviruses, I always tell people to do the snatch and rear technique. So remove those newborn lambs, those newborn kids right at birth, and provide powdered or pasteurized colostrum and milk. So those powdered colostrum replacement products don't always work the best. So it is possible to heat treat your colostrum as well to help kill the bacteria or the virus. When it comes to preventing Johne's, just keeping a really clean lambing pen, keeping feed and water troughs clean is also really important. Johne's can survive sometimes in the water, so that can be a big one, just trying to keep those clean. For Johne's, unfortunately, there is a vaccine for it, but it's not currently available here. So there is a cattle vaccine available in the States and a sheep vaccine available in Europe, but unfortunately we don't have them here. For our small ruminant lentiviruses, so again, removing those newborn lambs at birth, providing pasteurized or powdered colostrum and milk. Housing age groups separately can also be really important for this one. So if you can prevent that transmission right at birth and house all of those lambs together as they go through life, then you'll help reduce the risk of transmission from other members of the herd flock. And frequent testing and selective culling is also a really good strategy with this one because the tests for our small ruminant lentiviruses are pretty good. So if you get a positive test, you can be pretty confident that animal is infected. This might not be the best approach if your prevalence is really high. So if you're one of those guys that has a prevalence of like, I don't know, in the 80s, 90s, this probably isn't practical because you'll be culling a lot of animals. In that case, you can try and remove those animals at birth and then stop that transmission. And then in some cases, people will actually build a separate bar for positive and negative animals and try and build up the negative side. So moving forward, basically, you need to do some more research to confirm some of these results. You need to take a closer look at immune responses and stress responses and understanding these diseases because there's still a lot we don't know. But most importantly, we really need to develop sort of some province-wide measures to help control these diseases in the province of Ontario. And does anyone have any questions? Ready?
Oh, yeah. You have to,
Okay.
No, or yes.
Yeah, because this is 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, because this is 2. So this is bigger than that.
So this is this.
Question, thank you so much, Nancy.
It's asking which one of these is bigger than 1.27.
someone's
talking
doing
to their kids.
Oh, I mean, almost everybody.
Oh.
So, yeah, thank you so much, Nancy. Was a great review about.
Is it possible to still ask one question? Or?
Yeah, so now time for questions. Yeah.
I was wondering when they're checking for immune response to establish a breeding value, do they start by giving a vaccine, say, to all the flock and then pull blood to check for a response, or how are they doing it?
Yeah, so basically they vaccinate the animals. So they go through the first vaccination and then they get boosted at about 2 weeks later. And then they go in and what they do is they take a blood test for the antibodies. But the test to assess the immune or the cell immune response is actually an intradermal one. So it's almost like an allergy test on the sheep. So they come out, they just put a little bit of the antigen under the skin and they just measure the amount of swelling. So it's very similar to an allergy test you'd have at the doctor.
Thank you.
Any other questions?
I can do it.
Oh, okay. Any other questions for Nancy? Was very clear, Nancy.
I've given it a few times.
No, really was a very good overview. Yeah, it was very clear. People. Okay. Okay, so if we don't have any other question, we can. I think we can.
We will
Okay.
be done.
We are done. Probably we are hungry, all of us. So, well, then you can post the next webinar if you hear some, maybe we can share if they have some comments or preference, but we would like to.
So I guess one question we might have is whether this kind of timing is good going forward, if we're going to do more of these, whether you like it around the noon hour. Does that work for people?
It works well for me. I'm happy with the time. I don't remember the hours.
Okay, well, that's good. Okay, because I think the plan is we've got a few more sort of lined up.
Yeah, talk about more research going on, and then, yeah, we'll continue with other topics. But again, if you want that we cover a specific topic, you can send information to Delma in the survey, and then we will try to cover and find the best person to speak about this specific topic. But yeah, we are open for suggestions.
Yes. Okay.
Yeah.
I think we're good.
So yeah, if there are not more questions, I think we can conclude for today.
Yeah.
Yeah.
Sounds good.
Okay. Thank you so much for joining the webinar. Thank you again, Nancy.
No problem.
It was very, very good summary and overview. And see you next webinar.
Yeah.
Bye.
Bye. Thank you. So he said all we need to do is
Exit.
exit, but exit meeting for all.